to look at, like parameter. So like that's the first step. And the second step is more like usual Python C API, which, well, we don't have time to look into that, but that's actually pretty well documented in the Python documentation. Like, but just, so which file is it in? I forgot. CTOS, yeah. From term. So, at least for everyone I've seen that found out which function to look at, they also the error is when you go, yeah, thank you. Python next iter here. When you have an exception, it will return null inside the generator. So you bypass all of this. Oh. And we arrive in that case. The premise here, what most likely happened is the person who did that code didn't think that the iterator could generate an exception itself. So it doesn't check that an exception was raised. It just re-raise a new exception. So if you do that, it's like if in Python, you have a try except, and then you do raise another type of exception, you lose the original exception. So that's just the same thing in C. So here what's missing is you just should check with a py error occurred, I think. So C call gives you whether there is already an exception set. And if so, then you need to like raise an exception. Otherwise, you can just do that. You don't even need to raise exception, actually. Actually, you shouldn't raise exception. You should just propagate. Otherwise, you break the original stack.
Would there possibly be a bug if the exception is raised on the very last iteration? Because the count would have been increased, the I would have been increased to equal count.
I would think that you would put it up closer to the value that you actually called it, right? Right there.
I'm just trying to think of when the exception gets thrown and when is it that I gets incremented. If I gets incremented after the exception would have been thrown, then we're okay. But if I gets incremented before the exception is thrown.
Yeah, I think you're right.
No, that's fine.
Yeah, but you need to be careful where you.
So if he had 50 and there's a 42 as an exception.
If the loop still passes through once on the last one.
It's in the NumPy, core, SRC, multi-array, ctor.c.
Now the solution is not quite so simple anymore, is it?
Sorry?
Now the solution is not quite so simple, right? With the I, when does the I get incremented?
I don't think that's going to
No, but I don't think we should know that. Because the error will happen.
Yeah, but count gets updated before
No, not count.
What? No, I don't know how to do that.
Yeah,
Yeah. Does I get updated before or after? And so you may have a problem with the very last one.
all you have to do is set your E to 50 right there.
I would put that outside. Yeah, outside you.
Yeah, that's what we're saying.
Yeah, because if I is equal to count, then it's going to completely skip that.
Yep.
No, you can't put it in the loop, it has to be up to the.
That's fine. It will still have right. It would have been.
Yeah, you would still,
Yeah,
yeah.
no, so you just put that check in wherever you want it.
Yeah, put it there and then also.
And at that point, I need to look into. Yeah, they should work. Yeah. Oh. Should have configured VI. X np from either gem second. I think we need D type as well. No, you get the right exception.
There's done through the right thing. If you detect an error, then you get it done. After done, is that the correct check fire?
So I would certainly not submit the code as is. I would need to check exactly. I'm not so familiar with this function actually. I would need to look into the error handling at the end to make sure it does the right thing in that case. But no, you're right. I mean, I should because I don't remember the semantics of PyArray. I'm not saying that's the right fix. Like that's a logical fix for the actual logical error. But as for the detail of implementation, I will need to look into what the semantics of PyArray from iter are. What happens when you return an error? And I don't remember offhand, at least. So that's a good. When you deal with C, it's a good mentality to keep, right?
But you can change that does work for the last one. So if you change yours 42 to B49, it still calls that an exception.
Yeah.
So which one you said?
Yeah, your error message.
Change the error message also. If you want to see it.
It's fine, it works.
Yeah.
Yeah, it works.
Okay, I said it wouldn't. Okay.
It works.
Yeah, I was confused. Yeah, obviously. Yeah. Okay. Okay, so I took already enough time from Stefan. So, I'd like to summarize. The key point is not to remember all the details. Really, the main thing is really the main difficulty when you deal with the NumPy C code is to understand when you go from Python to C. That's really the main thing. So when you go from there, you have two different ways. If you're on a platform that has a nice tool like dtrace, well, then you can use dtrace. If Python integrates with dtrace, as it does on MicroSX or Solaris, then you can very easily get call trace at runtime. On Linux, you're a bit out of luck. On Windows, I have no idea. And then you have either you work from first principle, and really the main data structure for NumPy array is this PyArray type that I'm showing here. If you understand this, and you understand how to look into the different protocols in Python, which are well documented in the Python C API, you understand the vast majority of entry point between C and Python, with Python and C for NumPy arrays. The other ways is to use this hack with Valgrind or perf that there's this limitation of using statistical sampling with perf at least, but it can give you call trace dynamically. Hopefully at some point someone will have a tool that integrates Python and C well on Unix, but for now you have to use either methods. I don't know any other better methods to do these kind of things. Okay, thank you. So Stefan will talk a bit about universal function, which is the other big concept in NumPy core.
So if you managed to fix that bug in the previous session and you sent a pull request to NumPy, the software carpentry folks here would immediately know what's the next question.
It's 3471, the pull request.
The pull request? Huh. So what's the software carpentry question? Yes. How will we make sure this never happens again? So
That was my comment.
yes. So a pull request will not be merged into NumPy if it does not have a test, because these things are subtle and they come up again and again. So we have a massive regression testing library of about 2,500 tests at the moment. When we started off with NumPy 0.9, I think we had 100. So we've come a long way. All right, so the next session we'll look at universal functions. So universal functions are vectorized functions that operate on, well, one element at a time. You get generalized UFunks that operate on more than that, but for now we'll just focus on the basic UFunks. And universal functions, they take one NumPy element, do some transformation on it, and give you that operation as the output. It supports various standard NumPy features, such as array broadcasting. It can cast types for you. For example, if you input an integer array, it can automatically transform it to a float array if necessary. So every time you call something like, let me just scale this back up. So if you use construct two arrays, and you do x plus x, that translates to using the np-add UFunk. That UFunk has got two inputs, and it takes the it matches point-wise or element-wise. It matches up those two, and it adds them together. Another example might be something like cosine. So if you look at the docstring, well, I'm not in IPython now. In IPython, you could type question mark, enter, and you'd get a nice summary of the docstring. And it would show you the docstring of a standard UFunk. What's that?
Just do help.
Oh, yeah. It's been a long time since I used normal Python. All right, so there you see, there's the UFunk. So all UFunks are this built-in UFunk class, and they all behave in a very similar way. So let me show you an example of how to produce a UFunk in pure Python. So here I've got something called range sum that I've defined. It takes two numbers, a and b. It constructs the range between a and b, and it sums it all together. So if you gave it 2 and 4, it would construct the numbers 2, 3, add them together, and you get 5 out. So NumPy has got this function called fromPyFunc that takes any Python function and turns it into a UFunk for you. So here I specify range sum as its input, and I tell it that it's got 2 inputs and 1 output. And then that creates rs, and rs is now a UFunk object. So you can construct an array such as x, just some data, apply rs to x and x plus 1, and there you get the expected output. Now, like I said, UFunks also support a whole bunch of standard NumPy machinery. So here I provided pretty standard inputs, x and x plus 1. But if I supply x and x's transpose instead, then look what happens. I'm now providing a row vector and a column vector, and those get broadcast against one another, and the operation gets computed on all the different combinations. So this is the kind of functionality that you get for free if you implement a UFunk. Now, of course, you don't want to implement your UFunk in Python. It's just going to be really slow, and there's no sense to it, really. So what we'll look at now is how to implement a UFunk in C. Just a bit more about how you can call UFunks. They've all got a standard calling API, and it supports several keywords, some of which are listed here. And these are also the features that UFunks include. So for example, you can specify the out keyword, and that is where the data should go to. So if you run numpy.add on an array and you specify out, then the results will automatically go into that output. So this is especially handy if you're working on massive arrays. You don't want to make temporary copies, and you can ensure that the output goes to a pre-allocated array of your choice. If you don't want to compute the UFunk on all the different positions of your array, you can specify a mask in the where keyword. So that means the UFunk will only apply it in the positions where that mask is equal to true. You can also do some adjusting of the default casting behavior. So NumPy by default tries to, if you provide an integer, but the UFunk expects a double, it will automatically cast up. And you can adjust that. We'll see a little bit more of that just now. You can also say what you want the output order to be, Fortran or C contiguous. You can specify the data type that you want for accumulation. This is especially important in something like summation, for example. If you're going to sum a bunch of numbers, you want to do it with a fairly large accumulator. Otherwise, you might get rolling over of the numbers. So that D-type argument allows you to specify which types are used for accumulation. And then a little bit more advanced would be the sig keyword, which allows you to specify exactly which UFunk loop you want to use. We'll see more about that just now, and X object, which we'll skip. The output type of a D-type is determined by the input class with the highest array priority. So array priority is a member of the NumPy array class. And array priority is an integer. You can set it to any number you want for a derived NumPy array class. So here I've constructed two classes, strong array with an array priority of 10 and weak array with an array priority of 1. I assign S to a strong array, W to a weak array, and when I add those two together and I ask for the type, you see that it is a strong array. So the one with the highest array priority always wins out. You can do something a little bit more sophisticated if you want as well. You can. There are two methods that are considered on the input, array prepare and array wrap. So before the UFunk is executed on the input, array prepare is executed on it. Array prepare is provided with some of the context, so what is the UFunk being called, what are the parameters, etc. And once the input array has been prepared, it is passed to the UFunk. Sorry, it's the output, of course, that's being prepared, and the output is wrapped as well. So that allows you to do a little bit of pre-processing and a little bit of post-processing on your output, if you want to set metadata or something like that. Right, so if you look at any UFunk, so let's look at np.add, and you look at its types attribute, you'll see those are all the signatures that are supported. So add, you can, for example, specify an integer and an integer as input and get an integer as output. Or you can specify a double and a double as input and get a double as output. Yeah. Yes, so we're going to see how to do that now. You can extend that, definitely. So you can basically make any combination of inputs and any output that you'd like. So I also mentioned there, if a suitable UFunk loop exists, NumPy will also try to cast. You can set the casting behavior with a casting keyword, and you can set it to no, never cast. Cast only if the data types are exactly equivalent. Cast if they're of the same kind, or even do unsafe casting. So even go from complex to double or whatever. Then finally, UFunks can be called, all UFunks have these properties. So you can call all UFunks with reduce, accumulate, reduce at, and outer. So just to briefly run over those, reduce, in the case of sum, for example, you can see that squashes one dimension. So if you sum the rows of an array, that removes one dimension from the array. Accumulate is like doing cum sums, like cumulative sum. Reduce at is quite interesting because that allows you to specify where over the array do you want the function to be applied. So for example, say you take the numbers from 0 to 11, reshape them into an array of 3 by 4, and then you apply add to this input, as well as to to the input, but you use reduce at, and you specify 0, 1, and 3. What this does is it says you will reduce between 0 and 1, and between 1 and 3. On which axis? On axis 1. So axis 1 would be your columns. So we're going to be adding columns 0 to 1, 1 to 3, and NumPy implicitly adds the last one for you, so 3 to the last one. So that's then what you see here is we add the first two columns together. Sorry, that's not, is that happening there?
It's 1, 2.
What's that?
It's adding 1 and 2.
Oh, it's adding 1 and 2, right. So the indices are, it's everything up to 1, and then 1 up to just before 3, so it's like a range. So that would be columns 1 and 2, and finally the last column. Okay. And then you can also ask for the outer product that just takes all the combinations of everything in A and everything in B and combine them together. Right, so like I said, UFunks operate on a single element of the array, so you need to provide it with a kernel. This kernel will get a single slice, if you want, of the array, so it will get like a single vector to operate on, and you have to apply this operation on all the elements of that vector. And the kernel will always have this signature, so you'll have some input arguments, dimensions, steps, and data. Now, by default, you don't have to use data. We start off dimension 0. That's where the length of the array is stored. So n is equal to dimension 0. Your input and your output arrays, they are stored in arguments. And then the step size, that refers back to the strides we spoke about earlier. That tells you how many bytes do you have to skip in memory to go from one element to the next. So we've got steps for, or strides for the input and strides for the output. Then we just allocate some temporary variables that we're going to use. So we loop, we set I going from 0 to the length of the vector. You grab the pointer, the input pointer, and you cast it to a double. So that gives you the value you're going to be operating on. In this case, I'm writing a function to square things. So I'm taking my temporary variable, and I'm just squaring it, so multiplying it by itself. And then I'm storing the output at the position of the output pointer. Okay, and then I take my input pointer, and I move it forward by the strides, and I take the output pointer and move it forward by the strides. So just to recap what happens there, you've got a pointer pointing towards this vector. You grab the first element from the input vector, and you do your operation on it, and you store that at the position of your output vector. Then you move both pointers one forward, and you keep repeating that operation. Yeah?
So, wouldn't it be easier to double pointers for everything?
Well, the strides are specified in bytes.
Yeah,
So
why is that?
I don't know what it is. That's
Well, we have various types that aren't floats.
right. I mean, you don't know exactly what type you're going to be getting. So to have the signature general enough, I guess this is what you need to do. Okay, so that's your loop. And then you want to install that into a Python module so that it can be called. So importantly, you must call import array and import umath before you do anything. That sets up the NumPy structures. And then the call that you're going to be making is PyUFunk from FunkData. That takes this kernel of yours and it transforms it into a universal function. From FunkData requires the following. It requires you to specify all the functions. So you remember all those signatures I showed you? Each of those signatures are associated with one of these kernels. So if you want to do an operation that takes a double and gives you a double out, that's a single function. If you want integer to map to integer, that's another function. So all of those functions you'll put in this funks variable. Data we can keep empty. Types is where we specify, so for each of these functions, what would their signature be? So you have to specify all the input types and all the output types. So our function that I implemented, it just mapped a double to a double. So in this case, I'll just say double, double. So input type, output type. If you had more of them, you would have all their types listed here. Then finally, you just need to tell it how many functions am I providing and how many input and output arguments do I have. And then just some doc strings and so on. Yeah.
So the types of the, what if your functions are 2 inputs and make 1 output?
Yeah, so if you took 2 inputs and 1 output, you would have 3 variables here for every, 3 types here for every function provided. So you'd have input, input, output.
Oh, so the last one's always the return. Oh, yeah.
Yes, always input, input, output. You can actually have more than one return as well. So you could have input, input, output, output.
How would you tell just which ones the outputs?
So here you specify the number of input and output arguments, so it knows. Okay, so all of this, this is what goes into your module initialization. So if you want to see a full example, you can just click on that link in the slides, and there is the full example. So there you can see the kernel and the structure that defines funks, data, and types. And then here is the module initialization. So this is just a boilerplate code, and then I explained the most essential parts to you. So you can just copy this as is if you want to make a UFunk, and you replace the kernel, and you update the types.
So that just works you just created a new function to square a double array.
Yes, I mean, it's not a very useful exercise, but
I mean, if you want to do it work at any time.
if you, yes, so I'm going to get to that. So it's not always necessary to provide such a complex kernel. So the kernel is much more than we'd want it to be, right? If you just want to map a double to a double, it seems a bit overkill to have to specify the whole loop, increase the pointers, and so on. So NumPy provides quite a number of standard kernels that you can use, and you could just sort of plug in the core of the kernel. So here's another example where the kernel is literally just a function that takes in a double and produces a double. That's sort of the smallest core we can provide. So one number in, one number out. Simple enough. You also set it up with from, func, and data. But in this case, the function you're going to provide is pi_ufunc _d_d. So pi_ufunc underscore whatever, those are all the standard kernels that NumPy provides. And dd means it's a kernel that maps double to a double. And then in the data attribute that we specify, we tell it where it can find the actual kernel. So we tell it there that my function is square d. Sorry, this should have been kernel. That's a typo on the slide. This pointer should point to the function kernel. Okay, and what NumPy then does is it takes this function, and on every element of the array, it executes this kernel of mine. So that's quite a bit of less typing. And as long as there's a matching generic function provided by NumPy, you're good to go. I've listed a few here at the bottom. So one example would be pi_ufunc ff, that just maps float to float. Or there's ddd, which maps 2 double inputs to a single double output. And then here's an interesting one. 2 float inputs, 1 float output, and then it says as ddd. So that means that if you've got a function that takes 2 double inputs and a single double and gives a single double output, but you want to wrap it in a UFunc that takes 2 floats rather and gives out a float, then you can use that general kernel. And it will automatically do all the casting for you. Aha, these are not the latest versions of the slides. Let me just reload. Okay, so you asked whether you can provide support for multiple D types. And so you probably need a templating engine for that. And I'd recommend you probably not use the NumPy templating engine for that. It requires a lot of copying of the same code, essentially, because you need to provide your kernels for all the different types. And the kernels are typically almost identical, except for the types. And we don't have templating otherwise. So I wrote this example using Tempita. Tempita is just a little single Python file that you can download that does some elementary templating for you. So here's just a snippet from how you would do that. So the double curly braces, that's template language, and that just says that, okay, define the following C types, and there I listed all the different C types I wanted to support. So I want to support my UFunk for int8, int32, int64, float, and double. And then I wrote the corresponding NumPy D types here, so npy underscore and all the different types. So this is just in the templating engine, these variables are now defined. And then you say for each type in my C types, generate the following code. And there you can see the start of the kernel function again, except now I give it a name. So where I used to write square D, I now call it square int8t, or square int32t, or square double, or square float. So that will be the name of the kernel, and it will have the standard signature. Let me load the full example so I can show you the actual kernel. Yeah. Yeah, so this is now a template. I need to translate this template into actual C source code before I can compile it. And what we essentially have is a big for loop that's going to take this text and replicate it many different times, just with the types changed in the different versions. So you can see, for example, here I defined my temporary variable that I had as a double last time. In this case, it just becomes double curly brackets type. So it will be double, it will be int, it will be float, it will become all of those. Okay, so I think I've actually got that example here. So let's see if I can where did we put our stuff? Are they here somewhere, David? Where are the is the source here? No, the source of the slides, of the UFunk examples.
Oh, sorry.
That's fine. Okay. Anyway, so the point is that my setup.py file, I now just import Tempita, and then I executed on that file, which I called myufunks.c.template. So I executed, that copies that function many, many different times over, and the output is then what gets compiled into an extension. This is in the Git repository for our slides. Is that in the virtual machine? Yeah, should be there. All right, so for an exercise, what I'd like you to try and do is to construct a custom UFunk called Poly. Poly will take two arguments, X and A, and it will evaluate the polynomial x squared plus 3 minus ax plus 5. And then do a timing comparison between your new UFunk and the built-in version in NumPy. So if you just executed that statement in NumPy versus the UFunk that you just wrote, you should see a fairly significant speed up. What's that? Yeah, so if you just constructed an array x in NumPy, and you just wrote the expression x squared plus 3 minus, whatever. Just one more thing. So I did do an implementation of this in Python as well that you can find in the repository. And the Python version is just as fast as the NumPy version, or maybe even a little bit faster. So you have to ask yourself the question, when do you really want to implement a UFunk? So do not implement a UFunk if you simply want to process a bunch of doubles quickly. Write it in Python. It's 4 lines of code, and it does the job perfectly well. If, however, you need all the functionality that a NumPy UFunk provides, so the broadcasting and all those things, the casting, etc., put it in a UFunk. Yeah. All right.
Okay, thank you. I think I always like to use the 5 last minutes for allowing some general questions about the subject that has been explained. So if you have general questions, I don't know, perhaps about the future of NumPy or I don't know, libraries that you can link with it, or some curiosity that you have, yeah. We should leverage that we have developers here.
So I have a silly question. Well, it's not that silly. What do you use for the slides, to make the slides? Because it's very nice.
It's called Remark.
Remark?
Remark, yeah.
Mark?
Remark.
With an R.
R-E-M-A-R-K.
Right, thanks.
More questions? Yeah.
So it's not really a question, I guess. We're missing out on the writing a custom D type section. We've run out of time, have we?
So for the custom D types, it would be difficult to do it in 1 minute. What I wanted to say is we have sprint on Friday. Well, Saturday there's still Friday. There's still sprints, but I won't be there. But other people will be there. So the last section was on custom D types, and the example was to implement. So GCC implements in software a new quadruple precision, like a 16-byte floating point things that some people are interested in having in NumPy. And to do that, you need to implement your own custom D type with all this. So one of the things we'll be sprinting on Friday and Saturday is to do to start an actual production-ready implementation of that inside NumPy. So for people interested in that, I will be there on Friday. The slides are available that gives the examples. The repository where the slides and the materials have all the different examples step by step how to build your own D type from scratch. And yeah, again, we'll be there on Friday and Saturday to help people who are interested in just general question, or like they're actually interested in implementing the thing. And we'll be here, and other developers will be here to help.
More questions? Yeah.
So this is perhaps a subjective one. That's okay. So I wanted to ask, for those developers or users, what would you say NumPy does well, and perhaps what would you say NumPy doesn't do so well? And with this in mind, how do you think newcomers to the codebase can help push NumPy in a direction where it can be improved?
It's really easy to build and debug, as we see.
Some comments?
So yeah, first,
this will be a subjective answer. So if you ask different developers of NumPy, you will have different answers. And also, to be fair, I don't spend so much time on NumPy nowadays, so like I may not even be the best person. Like I haven't contributed a lot to NumPy the last few years, so that was a caveat. Conceptually, I would say the main limitation of NumPy is that right now, a NumPy has a single buffer. So it doesn't have to be contiguous, but it's a single buffer, which means that there's a lot of consequences. Like you cannot easily have a NumPy array on multiple, like address space on different machines, for example, because of that. Or you cannot easily have things like, we have sparse matrices in SciPy, but to be honest, it's kind of clunky. So conceptually, that's really the main limitation. In practice, you have a lot of other limitations. So like the UFunk, so I don't know, what was the order of magnitude difference between the polynomial? Like 3. And that's weird, right? I mean, it shouldn't be that much of a difference. A lot of the UFunk, there's a lot of code like that goes back and forth that shouldn't. Like there are some code paths that are really common that are not optimized. Like in terms of profiling, there's really a lot to do. So that's something I didn't have time to show today. But like profiling, there's something you can do a lot, like profiling and fixing like speed issues, like scalar arrays are really slow. Like if you have A, which is a scalar array, A plus A is like 10 times slower than if A is a float, Python float, which, you know, again, is not really good. In terms of indexing, so Wes McKinney, who is not here, who is the main author of Pandas, he will tell you that like some horror stories in terms of indexing speed difference, like when you call a different function that gives you the same output, you have half an order of magnitude difference, again, because of different code paths. And so in terms of like speeding up the existing feature of NumPy, it's something where people can do a lot of good. Like that's how I studied myself a few years ago. Like the clip function was really slow, and just like most of the case, you could have a fast code path that was one order of magnitude faster. And that's really the main thing you can do. And again, the sprint is a good occasion to do that. Maybe Francesc has some different answer to give.
I have different views on. I mean, everyone has different views of the problems, right? So another problem with NumPy, in my opinion, is that NumPy is forced to use the Python evaluation engine, in the sense that when you are evaluating complex expressions, you need to create temporaries in order to store the different temporary variables there. These temporaries can be very, very large, and these temporaries should be stored in memory. So there's two problems with this. The temporaries takes memory, and that's costly, and the time to store this data in memory is also very costly. So that reduces the speed also of NumPy. So yeah, that is also a limitation of this. And there are different approaches to try to that tries to solve this, but not NumPy. Yeah, one last question.
It's actually just more of a comment, but this discussion is interesting, and I think a lot of you would be interested in a bird of a feather that we are organizing on Wednesday at lunchtime. So it's going to be after the general session in 204, and we'll talk about the future of array-oriented programming and the different projects that are coming out and how they should talk to each other in the future. So
maybe you have one, or we're running out of time.
I'm curious whether there's, if you can comment on any plans for supporting really large arrays and some kind of tiling that's going on behind, because I love dealing with NumPy for, just at the top level, and rather than, I know it's not efficient I should implement my own tiling algorithm or something, but I'm wondering if there's anything that's out there that one could use that does tiling in the background or something.
For very large,
yeah, very large arrays. So you have, let's say, a really huge image, like a huge panorama or something that's in a NumPy array, and you have another one, you want to do some operation on it. So you can't hold all of it in memory. Is there something that can sort of tile it, do the operation in a tiling fashion?
Yeah. Well, I can answer part of it because, in effect, this is a very big problem. There are several approaches right now. For example, SDF5 could be a solution. SDF5 is a format that is stored on disk. But of course, you can store also datasets in memory. It has support for storing data in memory. And SDF5 is intrinsically a chunked dataset. So you may want, you can define the chunks on, for example, in your images, and then say, well, my chunks will be this rectangular size, and you can iterate over the different chunks. And the chunks can reside either on disk and either in memory. So this is the SDF5 approach, and also the data can be compressed and decompressed on the fly, which is really interesting. This is an approach that already exists, and that you can use that now. And we at Continuum right now are working on a different approach for doing the same thing, which is called, the library that we are working on is Blaze, okay? So with Blaze, you will be able to do the same things, but using also an optimized execution engine in order to optimize all the operations between the different data in the chunks. I am happy to say that we released Blaze 0.1 just yesterday night. Travis did the release. So it is not meant for production, but it's meant more for people looking at the code and looking at the future capabilities of Blaze. So if you're curious about it, you can go to blazepydata.org, and you can download the code and experiment with it. It's a preview technology. It's not something fancy, but you can preview it. Blaze is B-L-A-Z-E, yes, Blaze. Anyone has something to add to this? I think it's time for lunch. Okay, sorry. Yes, we should move. Okay, thank you very much, and let's thanks to the presenters.